Hello everyone, good afternoon and welcome to the latest ECA Technical Tuesdays webinar. Today's webinar is all about verification of Earth Fault Loop Impedance. Today we're joined by ECA's Technical Manager, Curtis Jones, and we also have a guest today. Welcome to Rob Barker, Director of Power Quality Expert, who is an ECA Commercial Associate. So today we're going to cover some of the key aspects, key considerations for verifying Earth Fault Loop Impedance when testing an electrical installation. I will shortly hand over to Curtis to kick off today's presentation. But before I do that, just a note to let you know that you should have on the right-hand side of your screen a question mark in a bubble. Please make use of that function at any time throughout today's webinar to ask your questions, and we will answer as many as we can at the end of the session. This session is accredited with ECA Professional Development, so you are able to claim a certificate at the end of the webinar. About an hour after we close the webinar today, you'll receive an email with your link to download your certificate and a load of extra resources and links from the presentation as well. So don't worry if there's any links you see pop up or Curtis and Rob mention any resources today. Those will be accessible in your post-webinar email later today. So that's it from me. Hope you enjoy today's session, and over to you, Curtis.
Thanks, Omar. Good morning, everyone. Well, afternoon, sorry now, everyone, and welcome to this presentation. So today, we're going to be looking at the topic of verification of fault loop impedance. Hopefully you can all hear me clearly and see the screen well. If there's any issues, please pop a message in the chat to Omar, and Omar can let me know. So on the agenda for today's presentation, so we're going to start things off by looking at chapter 41 of BS 7671, which of course looks at protection against electric shock. And in particular, we'll be looking at the protective measure of automatic disconnection of supply, ADS, which of course is our most common protective measure against electric shock. So we'll introduce things with that. We'll then look at methods of obtaining Earth Fault Loop Impedance readings. We'll look at inaccuracies that occur when measuring Earth Fault Loop Impedance. We'll look at high resolution test equipment for Earth Fault Loop Impedance testing. We'll look at the verification of the results. And we'll also touch on a sort of an introductory topic, a bit of awareness on the provisions where automatic disconnection is not feasible. And then, of course, we'll finish off with a summary, and there'll be an opportunity to ask some questions. I think it's worth pointing out before we get stuck into this presentation, Earth Fault Loop Impedance is a big topic. There's always questions around this. So can't cover everything today. I think you're sort of aim to be done in around an hour with questions. So there will be some things, of course, we won't cover. The presentation is mainly focusing on verification, so we won't really be looking at things from a design aspect in particular, and there won't really be any step-by-step procedures on how to physically conduct the tests. That is taken as assumed knowledge as part of the presentation. Okay, so before we get stuck into the presentation, a quick introduction on myself. My name is Curtis Jones, and I'm a technical manager here at the ECA. I've been with the ECA as a member of the technical team for around 15-16 months now. I sort of came into industry shortly after leaving school as an apprentice, so working out in the field in a variety of backgrounds, and I think probably the most important one based on today is I've built quite a strong experience with regards to inspection and testing in particular. After coming off the tools and prior to working at the ECA, I spent a few years working in education and training. So where I was delivering the apprenticeship framework, as well as courses on the wiring regulations, and many periodic and initial inspection and testing courses, so the 2391 as it's widely known. So that was sort of life before ECA. Obviously my sort of day-to-day, I work for the technical team, so you may have spoke to me on the technical helpline, obviously deliver presentations and write guidance, but alongside that, working at the ECA allows me to be involved with the development of standards, and in particular BS 7671. So I'm on a member of JPAL subcommittee C, which mainly looks at protection against electric shock, and that is something we are going to discuss today. Of course, us as the ECA, we are the UK's largest electrical trade association, and our members combined turnover around £6 billion annually. So as you can imagine, there's a lot of inspection and testing that's being carried out. So hopefully a bit of relevance with today's topic. So I'm just going to hand you over to Rob now, who joins me for today's presentation.
Yeah, hi, so I'm Rob Barker. I'm a ECA commercial associate. I'm also the authorised representative for Sonal in the UK. A bit about Sonal: they are 30 years old this year. They have over 100 distributors worldwide, and they have an annual turnover last year of around €50 million. My company, Power Quality Expert, apart from doing instrumentation, we also provide power quality harmonic surveys, load profiling, power quality report service to the ECA members.
Brilliant. Thanks, Rob.
Thank you.
Right then, so I'll kick things off with today's presentation, and we'll be hearing a little bit more from Rob further into the presentation. So introducing things, start things basic. A lot of this is probably going to be a recap more than anything. So looking at protection against electric shock. Now, chapter 41 of BS 7671, of course, covers this, and it states within the introduction there that the fundamental rule of protection against shock, according to BSEN 61140, is that hazardous live parts shall not be accessible, and accessible conductive parts shall not be hazardous live, both under normal conditions and under single fault conditions. So let's unpack this a little bit and look at how we generally achieve this. So we generally achieve our fundamental rule of protection against shock by using automatic disconnection of supply. It's our most common protective measure. So automatic disconnection of supply is broken down into two elements. We have what we call basic protection, and we have fault protection. So fault protection is provided by barriers and enclosures, as well as the insulation around live conductors or live parts like our conductors. So we have an example here of an enclosure, an image Hager have kindly allowed us to use of an enclosure being a distribution board here. We also then, as touched on, have fault protection. Now our fault protection is made up of protective earthing. So we have an earthing system for the installation, and then our circuits are all connected to the main earthing terminal at each point in wiring via circuit protective conductors, which of course is there to carry fault current. And then we have protective equipotential bonding, which of course we take to extraneous conductive parts that are liable to introduce a dangerous potential difference. So we're looking at things like incoming metallic water pipes, metallic gas pipes, structural steel, and so on. So that sort of highlights the difference in why we earth in terms of earthing and bonding as such. And then the other part of fault protection is the automatic disconnection in case of a fault. So it's about the circuit disconnecting from the system in the event of a fault within a specified time. So to relate that back to our fundamental rule that we touched on a minute ago, our basic protection ensures that hazardous live parts are not accessible, and then our fault protection ensures that accessible conductive parts are not hazardous live and both under normal and under a single fault condition. Okay, looking a bit deeper into the automatic disconnection in case of a fault element, and this is probably what we're going to focus on more today, with the subject being around Earth Fault Loop, verifying Earth Fault Loop impedance. So to achieve our automatic disconnection in case of a fault, a protective device is required to automatically disconnect the supply to the line conductor of a circuit or equipment in the event of an earth fault. And that's some information that I've summarised based on regulation 411.3.2.1. So we need a protective device to disconnect the supply to the line conductor when we get an earth fault occur. Now this is to occur within a specified time, and that time depends upon the type of circuit, the usage of the circuit, and the earthing system in question. So looking at the disconnection times. For final circuits with a rated current not exceeding 63 amps with one or more socket outlets, and up to 32 amps supplying fixed connected current using equipment, so again final circuits, then table 41.1 of BS 7671 applies. And again, this is in relation to regulation 411.3.2.2. So looking at the bottom of the screen here, we have table 41.1. So we can see sort of to the left of the table, it refers to the earthing system type. So if we had a typical TN system, and then we had a nominal voltage to earth, UO, of 230 volts, which is obviously what we generally have. And if our circuit was to be, as per this first bullet point, so let's say a piece of fixed equipment at 16 amps, maybe a heater, on an AC system, then our maximum disconnection time would be 0.4 seconds. Now the second bullet point on screen here covers the other types of circuits that are not covered by the first bullet point. So distribution circuits are covered, and other circuits, so maybe circuits that are fixed equipment of a larger load. So those circuits are covered by regulations 411.3.2.3 and 411.3.2.4 respectively, and they tell us for, let's say, a distribution circuit on a TN system, the maximum disconnection time is 5 seconds, and respectively for a TT system, 1 second. So this is how quickly our circuits need to disconnect depending upon the type, use, and earthing system in question. Okay, so how is it that we confirm these disconnection times? How is it that we know we are actually achieving the required disconnection? So we generally do this by confirming the maximum earth fault loop impedance for the circuit that is in question. So what is earth fault loop impedance? Now we've got on screen here an image which should aid to describe this. Now the earth fault loop impedance is the impedance of the earth fault current loop starting and ending at the point of earth fault, and this impedance is denoted by the symbol ZX. So here we can see we've got an earth fault loop impedance diagram. So we can see we've got an exposed conductive part here, which could be, let's say, a metallic light fitting, a piece of class 1 equipment. We've got the load connected across line and neutral, the light, and then we have a CPC connected to the exposed conductive part, connected to the earth of the system, of course. Now, if an earth fault was to occur, so the line conductor was to touch to the metal casing of the piece of equipment, then hopefully it's going to generate a sufficient fault current to cause this automatic disconnection and allow for a suitable disconnection time. Now this fault current will generate, and then it will travel back through the circuit protective conductor, back through the earthing conductor, and in this case back through the PEN conductor, with this being a TNCS earthing system. It will go back through the distributor's transformer, back through the supply line conductor to complete a loop, and then it should hopefully disconnect the protective device nearest the origin of the fault. So that just sort of hopefully describes what happens in the event of an earth fault, and in order for it to be suitable, we need the impedance to be of a suitably low value, which should then give us a sufficient fault current. Okay, so that's sort of the introduction done, hopefully the basics and the recaps. We're now going to look at the different methods that we can use to obtain Earth fault loop impedance readings. So we're looking on the aspect of a circuit here. So we're looking at when measuring circuits. The preferred method is to obtain a measurement of R1 plus R2 via a continuity test and add this value to the external Earth fault loop impedance, the ZA, in the case that the circuit is fed from the origin of the installation, or add the R1 plus R2 to the ZDB where the circuit is fed from a sub-distribution board. So that then gives us the total Earth fault loop impedance. I think just flicking back to the image I previously had, R1 being the resistance of the line conductor, R2 the resistance of the circuit protective conductor, and ZA the impedance based on the external part, the supply. So that's sort of looked at as the preferred method. The second method is direct measurement of total Earth fault loop impedance with an Earth fault loop impedance tester. So this is something we're going to focus on quite a lot today, in particular the direct measurement. So looking at the direct measurement, what things have you got to, some things to consider prior to looking to carry this out. Now you need suitable test equipment to carry out a direct measurement of Earth fault loop impedance, and this will need to comply with BSEN 61557 Part 3. You'll also need to consider that when you're carrying out direct measurement of Earth fault loop impedance, that you are going to be working near live electrical systems. So you're going to need to ensure that you are achieving compliance with the electricity at work regulations. So for you to be carrying out this live testing, it needs to be reasonable to carry out such works. You need to be employing suitable precautions to prevent injury. So realistically, if you can do it via a dead method, that may be a safer option and a more preferred option. But where it's required to carry out live testing, you need to ensure you are achieving compliance with the electricity at work regulations. ECA has a guide based on work on or near live low voltage electrical systems, and we will circulate the links to the guides that we refer to today. Now, direct measurement of Earth fault loop impedance is particularly useful when conducting periodic inspection and testing. It may be a case when you perform periodic inspection and testing, it's not possible to de-energize a system. So it is a suitable method for confirming disconnection times. Of course, it's not limited to periodic inspection and testing, but it is particularly useful for that. And obviously, where we have newer systems, it's a lot easier to carry out dead tests and confirm Earth fault loop impedance values that way. Okay, so next we're going to look at the inaccuracies that occur when we measure Earth fault loop impedance and some things that we would like to consider. So before sort of drilling down and looking in particular at accuracies, it's worth pointing out the general methods that are available for obtaining Earth fault loop impedance readings. So there's generally three methods, and they are listed on screen in order of preference. So firstly, we have what we call the two-wire high current test setting. Now the two-wire high current test setting, as stated, is the preferred. This is because it generates a large enough test current, typically around 25 amps with a standard multifunctional test instrument. We've got an example from Sonel on screen here. And this test current of around 25 amps allows to create a measurable voltage drop and consequently a stable and accurate reading. The test generally only lasts a few seconds, and the load is not present for no more than 40 milliseconds. So this is preferred. However, the issue with this test is that if we've got an RCD present on the circuit, it will trip the RCD due to the level of current that's going to be generated. It's also possible to potentially trip some smaller rated MCBs, some smaller circuit breakers. So we need to consider that this test is the preferred when placing measurements, but if we've got RCDs present, it wouldn't be a suitable method to select. So then next preference would be the 3-wire non-trip test setting, and finally the 2-wire non-trip test setting. Now the difficulty with the non-trip test settings is that the test current is significantly smaller than the 2-wire high current test setting. And this is typically not exceeding 15 milliamps. And this of course is in order to prevent the RCD or RCBO within the circuit from tripping. As a result of this, the test does not create a significant voltage drop. So therefore, many more test cycles are required, but this does result in a larger degree of variation in the readings that are obtained. So the readings are less reliable, they're more prone to variation. Now the 2-wire non-trip test setting in particular is the least accurate. It's the most technically difficult for an instrument performed, so should only be used where it has to be as such. So maybe it may be useful for circuits where there's an RCD present and there is no neutral present at the point you are looking to test that. Okay, so that highlights up some of the inaccuracies that can occur based on the different types of settings you're selecting when carrying out the measurements of Earth Fault Loop impedance. Now, something else to be aware of is something called RCD uplift. Now, what can occur here is when the measurement is carried out on one of the low settings, so the 3 low setting, for example, the test instrument may include the internal impedance of the RCD itself. So it's including the impedance of the coils within the RCD itself. Now, important to highlight that this is a may, it's not always, but it may include it on certain RCDs. Now, the issue with this, of course, is it's going to add additional impedance to your reading, and this could be up to around 0.5 ohms or maybe even more. Now, of course, that may give you issues when you look to verify your result. It may be a lot higher than you expect, and then you may be questioning that you potentially got a fault or an issue on your circuit. So this is something that inspectors need to be aware of. If, as an inspector, you suspect RCD uplift, a simple measurement can be carried out on the supply side of the RCD or RCBO, and then the same measurement repeated on the load side of the device. So if additional impedance is obtained on the load side of the device, this can then be deducted from the overall measurement obtained. So if this happens, if this particular circumstance arises, it's something to be aware of. There's a method of getting around it, as highlighted there. And I think it would be a good idea if RCD uplift is detected that you list that on the relevant parts of your certification, so likely within your remarks that you've encountered RCD uplift. It's worth pointing out, though, obviously technology is always evolving, and for some time now there have been some instruments around that are immune to the effects of RCD uplift. So we encourage you to consult your manufacturer's data, as your instrument itself may be immune to the effects of RCD uplift. And I think that's probably the first time of many today that we are going to encourage you to consult your manufacturer's data with the requirements and performance of your test instruments. Okay, so what other inaccuracies can occur when measuring Earth Fault Loop impedance? Now, we've already discussed that voltage is a factor and current. So things like external load switching will affect the voltage. It could cause a drop in voltage, which may cause inaccuracies within your reading. Electrical noise, again, it can affect voltage and frequency. So when we're carrying out measurements, circuits should be preferably be tested where there is no load present. We should be tested on a circuit where there is no load. Where there's load present, we may have things like semiconductors, relays, etc. Within the equipment itself. And this is more likely to create a noisy circuit and variations within your readings, particularly on those lower current test settings. Harmonics, again, this can distort the waveform, often caused by specific loads, VSDs, PCs, possibly lighting, and again, could have effects on your readings. Electronic components, I think I've touched on that one already. And then I think the final four things here, more basic things, but these can affect Earth Fault Loop impedance readings in terms of accuracy, but they can also affect other types of tests. I think one definitely to point out as it's relevant today is continuity testing. So if you've got issues with your test leads, they're damaged, you may see fluctuations within your readings. If when carrying out the measurement itself, you're getting a poor probe contact, again, you're going to be adding to your readings. Poor battery life can affect the performance of the instrument, so should be checked prior to the use of the instrument. And as well, the ambient environmental usage conditions that you are using the instrument in. Of course, it is when it's produced and checked, it's tested within certain parameters and certain temperature conditions. So if you're acting outside of that scope, or maybe at the lower and higher end of the scale, you may see some effects there. So there's some things to consider in terms of the accuracy and how it could be affected. Okay, and the final one that we want to focus on here, and we're going to dive a lot deeper into within this presentation, is where you are measuring impedance close to the source of the supply. So if we're measuring real close to a supply transformer, so this I think is particularly going to affect members maybe where they're working on installations or at the source of installations where we've got private transformers on site. Obviously, the fault current levels are likely to be a lot higher, so impedance levels are going to be a lot lower. Now, where this is the case, instrument measurements range, so the range that your instrument can operate at, and the resolution of the instrument, it may be inadequate for the circumstances that you are trying to use it for. So for that circumstance, you may need specialist test equipment, and we've got an example of a high resolution impedance tester on screen here. So that's where the next part of the presentation we're looking to focus on. We're going to have a look at high resolution Earth Fault Loop impedance test equipment. And I'm now going to hand you over to Rob, who's going to discuss this further.
Thanks, Curtis. Yes, so as Curtis mentioned, the standard for the accuracy of instrumentation or test equipment is BSEN 61557. So within that standard, it defines the permissible error measurement or measurement error of various types of instrumentation. So in terms of what we're talking about today, we can see that we're allowed a permissible error, a measurement error of 30% when we're looking at loop impedance, which on the face of it seems quite a high percentage. So to explain how we sort of get to that, or how we use that, we've got some examples to show you. So we can have the next slide, thank you. So in order to do that, we need to go through a few terms first. So we have the display, first off, we have the display range. Now this is, we typically call the count of the display. So typically, let's say, for example, 2000 counts, which will mean that your display on your multifunction meter will be able to display values from 0.00 to 19.99, then up to 199.9, and then 1999. We then have what we call the measurement range. Now the measurement range is where the manufacturer will state in the manual where they're comfortable or happy that their instrument will comply with the permissible measurement error. So in this example, we're saying that the instrument is fine down to 0.2 of an ohm. So anything lower than 0.2 of an ohm we're then going to be outside that 30%. We then have the resolution of the display. So typically on a multifunction meter, you'll see a resolution of 0.01. So as we can see in the display range at the top, where we had 19.99, that's where that resolution would apply. We then have the instrumentation accuracy. So this is made up of two components. We have an analog error and we have a fixed digital error. So the analog part is typically the percentage of the measured value displayed. And then we have a fixed digital error, which we would sometimes refer to as the digits. So in this example, we can see that we have a measurement range with a resolution of 0.01 of an ohm. And we're saying that the instrumentation has an accuracy of 2% of the measured value plus 4 digits. So when we have a displayed value of 1 ohm, the percentage of the measured value calculates out at 0.02 of an ohm. We then have the 4-digit error, which we always put the digit error on the least significant digit of the range. That total error summary would then come to 0.06. Now, if we divide that by 1 and times that by 100 to get the percentage, we'll see that that is a 6% error summary. On this type of equipment, we're looking at a lower displayed value. So if we're looking at 0.13 of an ohm, 130 milliohm, we'll see that if we divide that by 100 and times it by 2, we would get 0.0026. Now that doesn't round up, and there's not enough digits on the display to show that. So we would have 0.00 for the percentage error. We still have the 4-digit error. So we still add the 4 to the least significant digit of the display, which gives us an error summary of 0.04, which if we divide that by 0.13 and times that by 100 to get the percentage, we'll see that that is just over the 30%, and therefore it's outside the 61557 permissible limit. So in this instance, when you're looking at a lower measurement of resistance, you need to consider a higher resolution earth loop impedance meter. Typically, these will have a resolution down to 0.1 milliohm. Their measurement range can start as low as 7.2 milliohm, and the test currents can be up to around 300 amps. So if we look at this second example where we have an instrument with a resolution of 0.1 milliohm, we can again see that we've got an accuracy or percentage accuracy of 2%. And when we're looking at higher measurement instruments, we then start to see that it's still a fixed digit error, but we're specifically specifying that in this instance it's a 2 milliohm digit error. So if we now look at 130 milliohm, we can see that the 2% value of that calculates out to be 2.6 milliohm. We add the fixed digit of 2 milliohm in this instance, which gives us a total error summary of 4.6. We divide that by 130, and we can see that this time we're getting a 4% value. So again, that's well within the 30%. And again, when we start to go down to lower values, so 20 milliohms may be the sort of value you're typically seeing close to the source at the transformer. We can again calculate the 2% measured value, which would be 0.4 milliohm. Again, it's the same fixed error of 2 milliohm, giving us a total error summary of 2.4. If we divide that by 20 times by 100, we get 12%. So again, that's well within the 30% measurement accuracy that we need to comply with the standard.
Brilliant. Thanks for that, Rob.
Thanks.
So I think sort of just to bolt on to what Rob's kindly gone through there and sort of hammer home is that as an inspector, you need to be aware of the measurement range of the test equipment that you're using and any limitations it brings. So a display range, the display range is going to start at 0, but the measurement range is going to be above that point, and that's the sort of lower end it will measure at in order to comply with BSEN 61557. And of course, we do need to select instruments that meet that standard. So it's something to be aware of in terms of what environment are you testing in. This isn't going to apply all the time. You're not going to need that kind of test equipment all of the time. And you know, depending on the types of environments you work in, you may never need it. But if you are working close to source or at source and carrying out these measurements, then you need to be aware that your test equipment is suitable for such. You are using it as per the manufacturer's literature and within its scope as such. I think sort of the last thing to bolt onto this as well, just going back to something I just discussed earlier, is considering actually do you need to carry out a measurement. Of course, external Earth Fault Loop impedance values can be obtained by inquirer. So if you've got a private supply, a newly commissioned transformer, we'd hope that the people that have commissioned the transformer can provide you with that information if that's outside your scope of works. And then maybe if you're still working very close to source, you can conduct the other method via measurements of R1, R2 and calculate that way and so on. Not always the case, I understand, but it's something to consider. Obviously, if you are carrying out measurements, it's important to select suitable equipment. Okay, so now we've looked at methods of obtaining Earth Fault Loop impedance. We've looked at some of the inaccuracies that can occur, and then we've looked at where you may need to consider the use of high resolution test equipment. We're now going to look at the verification side of Earth Fault Loop impedance. So what you need to consider when you're looking to verify these results. Now, I'm going to base this initial part on a question that we quite commonly get through to ECA's technical helpline. And this question is often, which values do I verify Earth Fault Loop impedance measurements against? And it's often bolted on with a little bit more information, being, do we use the 100% values within BS7671, or do we use the 80% values in the guidance note 3? And on top of that, I guess the other question, which I'm going to look at here as well, is which one goes on to the schedule of circuit details? So which are the maximum values that you should list on the schedule of circuit details, your maximum ZS values? Now, sticking with the initial question, which values do I verify Earth Fault Loop impedance measurements against? It's a great question that we get. Unfortunately, there isn't a simple answer to it. However, we're going to look to unpick the question now over the next couple of slides, which then will hopefully give you the required information to be able to answer it, because the answer could change on a case-by-case basis depending on what you're doing. So let's just start with an outline, really, is that values of Earth Fault Loop impedance, they can be verified in multiple ways, including comparison against design information. So if you've got a brand new installation, it may be that you've got design information available to you for predicted values. You can verify them against the maximum values provided by the manufacturer of the associated protective device. So that is mentioned within Appendix 3 of BS7671, and you could say it's preferred because they're going to be more specific to the products you are using. And then I think the two that we're going to focus on the most here is industry guidance. You can verify it with use of that. So we've got the guidance note 3 on-site guide. And then, of course, we've got BS7671. So starting with the values of maximum Earth Fault Loop impedance in BS7671. So these are found within chapter 41, where we had a little look earlier, and they're found within tables 41.2, 41.3 and 41.4 for typical overcurrent protective devices, so circuit breakers and fuses, based on a nominal voltage of 230. Now, these maximum values of Earth Fault Loop impedance are based on some specific information or specific circumstances. And this information is listed within the notes below the table, which of course provide further guidance. And it tells us that the values within this table, or these tables, are based on the line conductors being at their maximum permitted operating temperature. And that's as per table 52.1. and then the circuit protective conductors being at their assumed initial temperature, again within the relevant tables in chapter 54. So if we take a typical example, we're going to say we've got a PVC thermoplastic cable, so typically has a maximum operating temperature of 70 degrees. Now, that's maximum operating temperature, so in order for that cable to get up to that 70 degrees, it's of course got to be under load, and it's going to have to be a considerable load. It's going to have to be at its maximum current carrying capacitor for that set of conditions. Now, as we know, when a conductor goes under load, it causes additional heat, of course, to get it up to that temperature. Now, one of the side effects of that is that additional heat means additional resistance, additional impedance. So when we're looking at the values within BS7671, the tables in chapter 41, they are based on those conductors being hot. So they have factored in that because they're hotter, there's going to be a higher level of impedance. Of course, when we measure earth fault loop impedance, some of the things we've pointed out today with inaccuracies, we preferably don't want to be testing that circuit where there's load present. If there's load present, it is potentially going to cause noise on the circuit and maybe make it a bit more difficult to get a more accurate reading. So preferably, we don't really want to be testing it with load on the circuit. So that needs to be considered in, can you use the values directly from BS7671? And we will revisit this shortly, where you may look to use them. So I think if you've got a circuit that's cold as such in temperature, it's brand new, it's never been turned on, and you've done a continuity test and got earth loop impedance that way, then you shouldn't be directly comparing against these values. Okay, so how are the values, how do we get these values of earth loop impedance within chapter 41? Now, they follow a formula based on regulation 411.4.4, which is ZS, or the max ZS, let's say, equals the nominal voltage to earth, UO, times by C min, which is a factor which takes into account voltage variations and changing of transformer taps and so on. So 0.95 that is, divided by IA, which is the amount of current in amps that causes effective operation of the device within a specified time. So that's how the values of earth fault loop impedance are calculated within chapter 41. Now, that calculation within appendix 3, or that formula, we can see again here, but there are some subtle differences that are added to it. So this is taken directly from appendix 3. And you'll see ZS now has an M, a little M by it, meaning measured impedance. And there is also a 0.8 factor placed in front of the earth, the formula that will give you the earth fault loop impedance value. So it's taking 80%. And so our ZS measured equals 80% of the values within BS7671. Now, this is to base it on ambient temperature. And these are the values that you find within the on-site guidance note 3. And it's based on the standard 70-degree cables being brought down to a temperature of 10 degrees. So often, particularly when we've got a brand new installation and we've done the R1, R2 method, and added to ZE or ZDB, it's going to be practical to compare against these values because, as we pointed out, circuit loading or the absence of circuit loading in this case means that the readings are going to be lower. So that's what that is based on, and that's where those values within the guidance note 3 and so on come from. So revisiting this question now. So recapping that, which values do I verify earth fault loop impedance measurements against? Now, we need to achieve compliance with BS7671. We need to confirm that our circuit disconnects. So that's our number one thing that we need to consider. Now, we may look at, is the design information available? If there's design information available, that's going to give you predicted values of earth fault loop impedance. So based on the design that was carried out, it would give you a predicted value of earth fault loop impedance. Now that's pretty useful because then you can compare, has that turned out as the designer intended? It's not a requirement to confirm against design data, but it's going to give you a good indication. If your value is considerably higher, you know, quite a bit higher, then it may signify that there may be something not quite right there. So there's that to consider. We then have manufacturer's data. Appendix 3 of BS 7671 encourages the use of manufacturer specific data. This will be less onerous than the values within BS 7671, so this is encouraged. If you do verify your readings against manufacturer's data, you should then attach that information with your handover pack, with your electrical installation certificate, or whatever document you're producing, and then detail, let's say, on the electrical installation certificate that the values were obtained via manufacturer's data. Okay, now the method used to obtain the value of earth fault loop impedance. So if you've carried out the continuity method, then it's very unlikely that you're going to be able to compare your value of earth fault loop impedance that you've gained directly against BS 7671, because it's unlikely that when you've carried out your continuity test that the conductors were at 70 degrees, let's say. It's much likely they're going to be cooler, so you're going to be comparing against the 80% values. But the next point is consider the conditions. Now, ambient temperature, yeah, if we're measuring that, it's generally going to be on-site guidance note 3. But circuit loading, as we've seen, is a massive factor here. It's going to cause heat. So for example, if you're carrying out an EICR, and let's say you've arranged to temporarily shut down a piece of equipment to conduct an earth fault loop impedance test to confirm ADS. Now that equipment may have been, it may be a piece of machinery or something that's been running for several hours. Based on that, the conductors could be at operating temperature if they're near to their current carrying capacitor. Now, if you momentarily shut that piece of equipment down and carry out the test, those conductors are still going to be hot. So you may then be able to compare your readings against the values within BS 7671. There may be other factors affecting your conductors. They may be run through a trunking system that has other live conductors that are also under load. Those are also going to have heating effects on the circuit that you're maybe carrying out your measurement against. So these things need to be considered. You could say as a blanket approach, oh, I'll just go safe and use the 80% values. That's fine. But what you've got to consider when you're doing an EICR is if those conductors are warm, you might not be able to achieve the 80% values. So it could be that you may be saying something's unsafe where you actually haven't considered the circumstances and the conditions. So I think this all stems down to now, as an inspector, you need to assess it on a case-by-case basis and apply that engineering judgment, taking into considerations the circumstances you've got. So hopefully that's give a bit more guidance on that common question. In terms of maximum earth loop impedance value permitted that you record on the schedule of circuit details, generally it's the value within BS 7671, although there is some notes under the table that says you can use other values. You just need to detail that you've used other values and where relevant, provide the relevant documentation. Okay, so last few bits now really. Obviously throughout the presentation, we've been focusing on earth fault loop impedance. We've been focusing on the basis of automatic disconnection using an overcurrent protective device, a fuse or a circuit breaker. Now, something else that often we see and sometimes we get asked is, can we use RCDs for fault protection? And the simple answer for that is yes, you can use RCDs for fault protection. Regulation 411.4.5 permits this. I think the most obvious example is where we have a TT earthing system. Impedance values are too high for overcurrent devices, so RCDs are employed maybe for additional protection, but maybe for fault protection as well. So that's your typical example of where it's employed. But there can be other circumstances. A designer may elect to use an RCD as their method of fault protection. They may have a device where they're, due to the constraints of the circuit, they're struggling to achieve the required impedance value. It may be very low. So an RCD can be used for fault protection. Designers can opt to do that. And where so, you can, the maximum disconnection times, the maximum impedance values should be verified against table 41.5 within BS 7671. Where that is the case, of course, overcurrent protection shall be provided in accordance with chapter 43. So we still need to look at achieving our overcurrent protection. I think the last little thing to bolt onto that one is, again, sometimes one we see is, can we just use the maximum earth loop impedance values for an RCD? If it's present, so it may be that you've got an RCD protecting a socket circuit that's also got a 32 amp MCB and, or fuse or whatever else. If the method of fault protection is via an overcurrent device, then you should be looking to confirm that the impedance value is below that. If your impedance value is high, it may signify a fault. It may be that you've got a loose connection, so it needs the consideration on why is it high, i.e. TT system and so on. Okay, and last thing to touch on now really is what about where we can't achieve automatic disconnection? And this is more of an introduction to and sort of raise awareness to that sometimes automatic disconnection is not feasible. Sometimes we can't achieve it with an overcurrent device, and sometimes we can't employ an RCD. So regulation 419.3 allows the provision of supplementary bonding to be applied by the installation designer. So in the cases we can't achieve ADS, we can use supplementary bonding if the designer elected to. If this measure was applied, then we would need to apply it in accordance with regulation 415.2. The IET guidance note 8 gives comprehensive guidance around this. So we encourage you, if you're looking at using this measure, it's something often missed, an option often missed, so it's just a raise of awareness on that. So we encourage you to consult the guidance within guidance note 8. And ECA does has a guide available to members for supplementary bonding too. Okay, so to summarise off, inspectors need to be aware of appropriate techniques in order to obtain accurate readings when performing earth fault loop impedance testing. Inspectors need to apply sound engineering judgment when verifying the readings obtained, and suitable test equipment should be selected, and specialist instruments may be required when measuring close to the source of a supply. Further reading on this, we have an ECA guide which should cover similar information and more based on verification of earth fault loop impedance. So I'll now come back to Omar to see if we've had any questions.
Thank you very much, Curtis, and thanks once again to our audience for attending today. Just before we jump into the Q&A, I'll just remind you that you will receive an email about an hour after we close the session today that will contain a link to download your ECA Professional Development Certificate, as well as the resources that we mentioned here today in the presentation, so you'll be able to review those. I should also mention that today's presentation has been recorded, and the recording will be available via the members section of the ECA website within the next couple of days, so keep an eye out for that as well. So we've got quite a few questions from the audience. There's a couple of ways we can go about this, Curtis and Rob.
Yeah.
Some of these are quite technical questions. They may be beyond my comms and marketing expertise. So what I've tried to do, Curtis, is I've tried to forward them through to you on GoTo. So let me know if you can see that. If not, no worries at all. I can read them out on my end.
I don't know if I can. Do you want to just go through them if that's all right?
No problem at all. Let me just bring them up here on my end. Here we go. All right, so first question, can I use ZE readings by calculating from the HV transformers plate?
Good question. I believe so, because it can be obtained via calculation. Let me confirm, but I'm pretty sure yes. I'm pretty sure the answer is yes to that, but I do want to confirm that. But
Yeah.
I'm pretty sure yes. So can you send me that, Omar, and the member's name just so I can confirm?
Absolutely.
But I believe
Yeah.
so.
Any questions that do require a bit of follow-up or extra reading on our part, we've got your email addresses and your questions. We'll be able to follow up with you individually after the session. No trouble at all.
Yeah.
Okay, so next one here. Do voltage variations play any effect on the measured value of EFLI?
Bob, do you want to do that one, or do you want me to give my thoughts?
I mean, it could. Yeah, I mean, for me,
different.
yeah, I mean, it can depend on how. It would probably depend on how the instrument is actually taking it. I mean, some instruments will take or will measure the actual voltage live during the test, whereas others will use a nominal value. So you would take, so these, we're measuring on a 230 supply, so it will use 230 as the calculation. In terms of sort of the higher current measurements that we're involved with, we're taking a specific, we use a 4-wire lead method. So we actually measure the voltage separate to the current on the handheld meters, or the multifunction testers with them only being 2 leads. That inaccuracy could be there, but again, it would depend on the manufacturer and how they're actually interpreting the voltage value. So
yeah, I think to bolt on, my understanding was, I think it probably the question comes from some of the points I made earlier around some of the basic things that will affect your reading. So my understanding is with some instruments and why some of those points were there was based on, yes, it possibly can, depending upon the instrument used, just to bolt onto that.
Okay. I've got a couple of questions here about Mega device. So we may or may not be able to cover this one. When our Mega was calibrated, the lowest applied reading was 0.637 ohms at 2 HI current. Is that enough for measuring readings as low as 0.04 ohms?
Do you want me to go first, Rob, and then you add in what you want?
Yeah, I mean it's it's a 0.63. So you would, in terms of what I've talked about, you would need to check the measurement range of the instrument to make sure that it's accurate at that level. In terms of a calibration certificate, the calibration house will apply a known value and take the measurement from the display. Now, if that measurement complies to the accuracy specification, then they'll still pass it. But whether that's within the measurement range that complies to 61557, you would have to double check with them in order to make sure that that is correct.
Yeah, my take's the same. You need to consult your manufacturer's data. I couldn't comment on a specific instrument that you will see either on the side of the instrument itself. It may show the measurement range, or if you actually get the handbook, it will tell you within there. So it will tell you the measurement range to BSN 61557-3. So it is a case of manufacturer data, just confirming that it only really becomes a big factor where you're really looking for these low level values. I think one point I didn't discuss today, me or Rob, that being, is you may also see within your manufacturer's data that when you look at the low test setting, the readings for accuracy are even higher. in terms of the levels, how low you can measure on the low settings. It's not that low, because as explained, the accuracy is more difficult to obtain. Does that sound right to you, Rob? What I've explained there? The low setting, the scale isn't as big basically on the low setting.
Yeah, so essentially what I say, so the measurement range is the important one to consider when we're looking at sort of instrumentation and selecting the right piece of equipment. So again, that's completely manufacturer specific. So the example that we gave in the presentation, we said 0.2 of an ohm as the measurement range. You might find that your instrumentation starts at 0.3 or 0.7 or even 1 ohm. It is that varied. In terms of the display range that we talked about, so where Curtis is saying that the lower end, you could have on a 2000 count display, we did say 19.99. You could have a range which would be 0.000 up to 1.999. So that in theory would give you a resolution of 0.001. However, where on those sorts of display ranges or measurement or display range, or the display range accuracy would then potentially be, let's say, plus or minus 5%. And it would then be plus, say, 0.0, I think we use 2 as an example, so it could be 2. Yeah. So at that point, even though you've got that lower range, display range, your inaccuracy is still going to start at that 0.02 level plus the percentage of the measured value. And that's when you sort of see the differential, the sort of the higher percentages in relation to the allowable permissible measurement error. So in terms of the calibration certificate, as long as the calculation works out, I mean, the measurement could be 120% of 61157, but if that's what the specification allows, then the calibration certificate will probably pass it as a within tolerance, but that's different to the measurement range. So hopefully
that's our bottom line, isn't it? Check the measurement range for the conditions you're using it. You're probably not going to have a problem in general. It's just for those members that are working, where there's higher fault currents present.
Yeah. I mean, there are, let's say that when you do read the manual, there can be some caveats to, the accuracies and the measurement ranges. So, for example, if we say, our multifunction tester, we do have a lower end measurement range, which is 0.019. It starts at. However, that's to the standard, but you need to use the 1.2 meter test leads, which are Sonel's leads. So again, there's caveats to those lower end on some of the sort of the more multifunction testers. When we're looking at specifically meters like we've shown today, the higher current models, it's because we've got a higher current measurement, we can be more accurate. So yeah, it's sort of what we said, check your measurement range in the manual. If it's not in the manual, ask the manufacturer what it is, and then work to that. And then anything below that measurement range, you really need to, I think me and Curtis have talked about this, you need to consider, is it actually accurate? Is it, or do we need to be looking at this with different instrumentation?
Yeah. And I think that answer would apply to a couple of other questions we've got here in the Q&A, referring to specific bits of equipment. Refer to the manufacturer's manual, the manufacturer data.
Yeah, so I'll say, so you'll have, typically when you're buying a piece of equipment, you'll get the data sheet, and the data sheet is sort of the sales literature, which shows you all the, the great things about the meter. So you might have a measurement resolution of 0.001, which is great because that's the display resolution, it's not the measurement range. So when you selecting a piece of equipment, you really do need to look at the manual if it hasn't stated that, and it will be in there if you look typically at the back, but if not, contact the manufacturer.
Absolutely. Thanks, Rob. I realise we have overrun our time slightly. Curtis, Rob, if do you have time for another couple of questions? And hopefully our audience has time for another questions. Those in the audience, if you do need to leave, that's absolutely fine. That will not prevent you from receiving your email with your certificate later on. So we'll just do a couple more questions. Let me scroll through here. And any questions that we weren't able to get to today, apologies. we will get back to you individually with those couple of questions that we've missed. Okay, so if a circuit protected by an RCBO has a higher than permitted EFLI, should a measurement be carried out between LN as well to check the overcurrent protection operates as expected in the event of a short circuit?
So higher than, let me just think now, I'm trying to unpack that one. So higher ZS, so it may, yeah, okay, I'm assuming higher than for the overcurrent protected device is what they're referring to there. Should a short circuit test be conducted? Right, there's no, so one thing that often gets confused here is disconnection times. So those disconnection times only apply to earth fault conditions. Those are maximum disconnection times based on an earth fault line conductor touching earth. So that 0.4 typical, 0.4 seconds typically is based on disconnection of earth fault. There's no actual disconnection time required for a line to line or line to neutral fault. That would be based on regulation 434.5, which looks at characteristics of a fault current protected device. So you've got what I'm sure a lot of members are going to know what I'm going to say now, adiabatic equations in there. And the speed in which a protective device needs to disconnect in short circuit conditions would be based on the adiabatic equation of T equals K squared times S squared divided by I squared. So it's looking at how much time have you got before thermal damage occurs to the conductors. So that would be the time. So realistically, generally not a requirement to measure it because of confirming a disconnection time. Hopefully that answers it.
Thanks, Curtis. We'll do one more question and then we'll close for today. This question is an interesting one. It's from a gentleman who is a chartered building surveyor who often has to read electrical reports. They're asking, how much does the earth loop impedance depend on the quality of the actual earthing into the ground?
Well, yeah, if your incoming earthing, if your incoming impedance is high at origin, it's obviously going to affect the results that you obtain within your system. So if your network or your supply of earth is poor, then that's going to affect all of your circuits, and could be a big issue within your installation and achieving disconnection for your circuits. Hopefully that covers that one. So yeah, it's important, the quality of your supply earth, because it's going to affect all of your circuits.
Yeah. Okay, we will wrap up there for today. Apologies again for overrunning slightly. Everyone stay tuned for your emails in about an hour's time. Do check your spam folders in case we end up there. Like I said, the link to download your certificate for today and any extra resources that we've mentioned in the presentation today. That's it. Thank you very much, everyone. Thanks once again to Curtis and Rob for joining us today. And stay tuned for the next Technical Tuesday webinar. It will be in early December. We don't have a date nailed down just yet, but keep your eye on your inbox for more updates there. All right. Thank you very much, everyone, and have a great afternoon.
Thank you.
Thanks.